Here in section 2.1, we're going to be taking a look at relations and functions. We have three objectives. Number one, identify relations and their domains and ranges. We'll do the same thing with functions as well. Identify functions by definition and by using the vertical line test. And then the last thing is evaluating functions in functional notation. Taking a look first at a relation is a set of ordered pairs. Now remember what an ordered pair is a coordinate, a point. Made up of an x and a y. And so here we have four of them. When we talk about an equation, it doesn't look like it's an ordered pair, but remember, equations are graphs of some sort. This would be a linear equation. And a line, if you think about a line is made up of an infinite number of dots. And so if we had some kind of graph like this, where this is our x, this is our y, that line right there is made up of an infinite number of dots. Dots are ordered pairs, therefore it's a relation. From there, we need to take a look at what a domain and what the range are. And when we take a look at domain and range, what a domain is connected to is the x value of a set, and the range is connected to the y values of a set. And so very easy when we talk about a finite number like these up here. It's a little bit tougher when we talk about an infinite number of ones, what our domain and range are at that point. But that's what we're going to be looking at first, is how to identify the domain and range of relations. And so graphing a relationship, identifying the domain and range, that's what we're going to be taking a look at right here. And so let's talk a little bit about graphing these ordered pairs when we have the two different types. We either have what they call a discrete relation, or we have a continuous relation, which is over here. So let's look at the discrete one. This word discrete just simply means finite, countable. Or that's how we're going to remember it, is when we have discrete, the set is finite, it contains a number. When we see this, we do not connect the dots when we have just a set of ordered pairs like this. This is 4 dots. The only time we connect the dots is when we deal with equations, and we'll talk about that over here in just a moment. For right now, let's go ahead and plot these points. 1, 3, remember this is your x, this is your y, so I go 1, 3, put a dot. -1 is my x, here's my x-axis, here's my y-axis, so my x I go -1, 4 is my y, I go up to 4, there's my second point, 3, 3, and then 4, 5, will be right there. So as much as we may want to connect these dots, we never ever connect the dots to a discrete relation. Even if the dots fell like in a perfect line, even if it's like this, it looks, oh, I want so badly want to connect those. Never, don't connect them. The only time you connect them is with an equation, not as a discrete relation. Now, when we want to identify the domain and range, remember the domain are your x values. Very easy. We've already labeled one of them. It's right there. So the x is 1, -1, 3, and 4. Now, what you want to do is you want to use set notation, which is your braces, and then we'll put it just into the braces like that. Now, the order that you put it in, you know, the -1 probably should go first. It doesn't matter. If you put it in like this, I'll give you credit. But technically, -1, we like to go from smallest to largest. Not a huge deal, though. If we take a look at the range, again, the range are going to be your y values. And so our y values are going to be here in black. And so what you have here is you got 3, 4, 3, and 5. Now notice I said 3 twice. You only need to list it once. You don't have to list it twice. And there you go. There's your domain and range. Very easy problems, those discrete ones. The ones that give us a little bit more trouble are the continuous ones. Now first off, continuous. How do I recognize it's continuous? Continuous has an equal sign. If it's an equation, then it's going to be continuous. If it doesn't have an equal sign, there's a good chance it's going to be discrete. Now, what tool can we always use to help us graph really any equation? And that is a t-chart. And so that's something we're going to be using a lot in Algebra 2, is a t-chart to help us out. It's a table of values. It allows us to take a sampling. That is the key, is remember that a t-chart is a sample. It's not the entire thing. We're just getting sort of a sample, some examples, so that we can sort of connect the dots at that point. Equations mean connect the dots. So that's an important concept right here. Anytime you deal with equations like this right here, we're going to connect the dots, and hopefully it makes a nice looking relation or function. So here y equals 2x plus 1. If I wanted to graph, now some of you may know slope-intercept form, go, roll. For those that maybe don't recall that, we'll be taking a look at it here later in another section. But for right now, let's use a t-chart. And how we use that is we take a sampling. We take maybe a positive. Let's do number 1. And then we use like maybe 0 and then maybe -1. I encourage you to use 3. You only need 2 for a linear equation, but if you make a mistake, you'll never know it. So I encourage you to use 3 points. It doesn't matter what 3, you just pick whatever 3 you want. So what I'm going to do is I'm simply saying this. I'm going to make x 1. And I want to see what y I get. And what you'll notice here is you get 2 plus 1, which is 3. And so there's an ordered pair, 1, 3, and I can put a dot. I do the same thing with 0. I plug in 0 right here. I get that goes away with 0 plus 1 is 1. There's another ordered pair, 0, 1. So you can see where right now I'm already ready. Let's make sure, though, with plugging in negative 1, I get negative 2 plus 1, which is negative 1. Let's see if that falls in line. Oh, look at that. That's amazing. Okay, and so there we go. Now we can connect the dots. You connect the dots with equations. You do not connect the dots with relations that are discrete. And so there we go. We have our linear equation graphed. Now, once we're done graphing, we are completely done with the table of values or the t-chart. We're done. We're done with that. I don't even want to look at it. A lot of students, what they do, here's a pitfall. What they want to do, a stumbling block here, is they want to look at the t-chart to see what the domain and range are. They go, oh, it's 1, 0, negative 1, right? No, those are just simply a sampling of the domain and range. Remember, you can pick whatever number you want. The domain here, I want to know what everything is. So here's how you do this. And this is what always given students trouble in the past, is the domain and range of continuous functions. But let's see if I can explain it. The domain is going to tell you how far the left and right your graph goes. So if I ask you that, if I say, okay, this, the arrow means it goes this way, right? It keeps just going that way. This keeps going that way. How far to the right does it go? Well, if you keep doing that, doesn't it go forever to the right? So if you take a look, forever means infinity. Okay, forever. If you go, in this case, how far out to the left does it go? Well, up forever, and so you got negative infinity. So it covers everything. It covers everything from negative infinity all the way to infinity. It's all real. So your domain in this case, for this example, is all reals. To be honest with you, for every linear equation, especially linear function, other than a vertical line, every linear function, your answer is going to be all reals for the domain. The only linear relation that you would get that wouldn't satisfy that all reals would be a vertical line. Okay, range. In this case, we want to know how far, not left and right, but how far up and down does your graph go? Well, how far up does it go? Well, it looks like it goes forever. How far down does it go? Well, it goes forever. Same thing, all reals. And again, for a linear equation, other than a horizontal line, you would get all reals. So you're going to get a lot of all reals for the linear equations. But we could have parabolas. We could have other types of graphs that we need to make sure we understand. And these are very important concepts here, is the domain and range, how far left and right for the domain, and how far up and down for the range. Okay, let's go ahead and take a practice problem with really 3 unique ones. Horizontal, remember horizontal lines, horizon goes this way. Vertical, go up and down. Okay, and a parabola is like a U-shaped or an N-shaped, so it could look like this, or it could be on its side. It just wouldn't be a function. So this right here is a parabola just on its side. Okay, but you can get an N-shaped. Any of those would be fine. So let's take a look at some of those. So I'll sort of graph these. Let's look at horizontal first. Let's say we have y equals 3. This is y equals 3. Horizontal line at 3. And they say, okay, you graphed it very good. The y's never change. Y is always going to be 3. So the x is going to be anything. This is your equation right there. So if I want to know what the domain and what the range were for the horizontal, I would simply say, well, how far to the right and left does it go? Well, it goes to the right forever and it goes to the left forever. So domain's going to be all reals. The range is how far up and down. Here's the tricky part. The range tells me my y values. Look what it says right here. Y, and let's put an English word here, is. Okay? Y is 3. So if y is 3, can it be anything else? Well, of course not. Y is 3. So the range, which are your y values, it has to be just 3. How far up and down does it go? It doesn't go anywhere. It stays at 3. 3 is your y. Okay? Let's go ahead and take a look at the vertical and see what we have here. So vertical line, let's do one like this. And this is x equals 2 is the equation. Notice that x is always 2. And they say, what's the domain, what's the range? Okay, and we say domain is how far right and left does it go. Well, it doesn't go to the right at all, it doesn't go left at all, it stays right at 2. Again, x is 2. Domain are your x's, domain has to be just 2. Range, how far up and down does it go? Well, it goes up forever, it goes down forever. This one's your all reals. Okay? If you used interval notation, which we've talked about, here's how you do an interval notation. Negative infinity to infinity. Okay, so if you want to be, you want to use some of that type of notation, that'd be wonderful. You can do that, and no problem. Okay, let's take a look at that last one here, and that's a parabola. And see what we can get here. Not the best, but not bad. Okay, so we'll take a look at this parabola here. And I went ahead and put the vertex down here. So somewhere right in there at -2, it goes down to -2 here. Okay, so if we wanted to know what its domain and what its range is, okay, so again, we will go back. Domain tells us how far left and right does it go. Well, with parabolas, it looks like it'll never go straight up. It'll never go straight up. It actually is always continually going out like this. So the further you can go, up, the further it's going to go out in this case. And so what we have is this going to go to negative infinity, while this one's going to go to infinity. So our domain is actually, once again, all reals. It's our range that we have some issues with, or some differences from what we've already done. How far up does the graph go? Well, it goes up forever, right? It goes up forever, so that's good. It goes up to infinity. But how far down does it go? Well, it stops right at -2. So in other words, what we have is from -2 to infinity is our range. How do we express that? Well, if you use interval notation, it's really not too bad. -2 to infinity. In algebraic notation, what you'd use is an inequality. And you'd simply say your ranges, which are your y values, are greater than or equal to -2. So whether it's interval notation or algebraic notation, you're now eligible or able to find the domain and range of these types of functions. Okay? Now, when we talk about functions, I just used the word function. Let's talk a little bit about functions. And this is a key thing you need to be responsible for, is what is the definition of a function. The function is a special type of relation where each element in the domain is paired with exactly one element in the range. That needs to be down. That is the definition of a function, and you're going to be able to determine if things are functions by that definition. Now, what does that mean? Well, what it means is that it means that every x domain, each element in the domain, so each x is only paired with exactly one y. That's the element in the range. A great way of remembering this, it's not a formal definition, but it's a good way of remembering, is that the x's can't cheat on the y's. And we talked about in class where, look, the one thing as a guy I know is that for my relationship with my wife to function properly, then I know I cannot cheat on her. So the x is the guy, the y is the girl. And for the relationship, because remember what a function is a special type of relationship. What makes it special is that the x's don't cheat on the y's. And so what we have here is we have a relation right here. It's a set of ordered pairs. But is it a function? Is it a special relation? Well, how do we determine that? It's by the definition. Do any of the x's cheat on the y's? This x is tied to the 3. So the 1 is tied to the 3. If the 1's tied to anything else, it's not. -1's tied to the 4, the 3's tied with the 3, and the 4's tied with the 5. So in this case, notice that none of the x's are duplicated. They don't cheat. This is a function. Yes. Now a lot of students will perk up here and go, whoa, 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 wait a minute. You got a 3 here, you got a 3 there. So the y is cheating. Look, I'm speaking from a guy's standpoint. All I can say is this: the x's can't cheat on the y's. That's what makes it a function. So the y's technically can cheat on the x's, but if it's going to be a one-to-one relation we'll talk about later, that's when the x's and the y's, neither one cheat. But in this case, we're only looking at the x's, and the x's cannot cheat on the y's. So if you look down here, if I said, hey, who's the cheater? It should be 1. 1's cheating. Tied to the 3, tied to the 5, not a function. Not a function. Okay. Now, here's sort of a graphical representation of what we're going to be doing. And what we have here are some ingredients. We have ingredients. These are the domains. This is what I'm going to plug into a function. What's the function I'm going to take these ingredients and plug into? Well, I'm going to put them in a blender. So if I take the right ingredients and I do the same ingredients every time and I plug it in here and I hit a button, boom, and it goes, then what I'm going to hopefully get is this delicious strawberry smoothie. And the result is what we call the y, or the range. And so this is sort of an example of how we do functions, whether it's in math or whether it's in computer science or whether it's just making a strawberry smoothie. We have something that we plug into a function. The function performs some operation, and then all of a sudden it produces something. And it better produce the same thing each time, because if it produces something different, then we're in trouble. So if it produced a hamburger instead of a milkshake, then you know, it'd be really cool, but unfortunately we would say that this is not functioning properly. It's spitting out some type of cheeseburger instead of a strawberry shake, which is what we were hoping for. Okay. Now, when we are trying to organize our information and recognize if it is a function, a lot of times we use this idea of mapping. I just want to show you this. We'll go through it fairly quickly here. A mapping shows how each member of the domain is paired with each member of the range. So here we have a relation. It's a function, because notice none of the x's cheat on the y's. But if I want to map them, we put all the domains over here, all the ranges over here. So, and then what we want to do is go from -3 to 1. Then I go from 0 to 2. And then I go from 2 to 4. And that's called mapping. Now, we call this a one-to-one function because the x's, so the x's and the y's neither cheat. And that's called a one-to-one function, when they neither the x's or y's cheat. This one, however, we do have a function. -1 goes to 5, 1 goes to 3, and then 4 goes to 5. So notice that all the x's only have one branch. That's fine. That makes it a function. It's not going to be one-to-one because this 5 has 2 of the domains. But it is a function. That's key. X's do not cheat on the y's. Over here, what you notice is we have 5 goes to 6. We have -3 goes to 0. We have -3 goes to 6. And then we got 1 goes to 1. There's your cheater right there. Okay, you got an x that's going to 2 y's, not a function. And so that's how we can identify, by definition, if it's a function. And what a one-to-one function is where the x's don't cheat and the y's don't cheat either. Let's go ahead and take a look at some examples really quickly, and we'll work through these fairly quick, so you can rewind if you need to. It says state whether each function, it's a function or not, and then for each function list the domain and range. So first off, is this a function? Well, do any of the x's cheat? No. Okay, so what's the domain? The domain in this case is going to be 2, -5, 8, and 1. Those are my x values. What's the range? Ooh, that was ugly. Let me read you that. That was ugly. There we go. And then our range are our y values. 1, 12, -3, 5. 1, -3, 12, and 5. Okay, there you go. We'll be doing the same thing. The domain and range, I'm not just concerned with the domain and range. We already done that. Let's just talk about if these are functions or not. How about the second one? No. This is not a function. So this one was yes, it is a function. This is no, it's not a function. Look at that. Okay? That is definitely not going to be a function. What it is it's actually going to be 4 dots that are vertically placed. If we take a look at this third one, is this a function? Well, the 2's cheat. So this one's a no as well. The last one, 3, 2, 1, -2. Yep, you're okay. And notice, even though the y is all 4, okay, the x's aren't cheating. So yes, it is a function. Now, is it one-to-one? No, it's not one-to-one. Okay, so it's not one-to-one, but it is a function. Last thing we'll be taking a look at here is identifying functions graphically and functional notation. So we want to look at, okay, how do I identify functions graphically? If they give me a graph instead of a set of ordered pairs or an equation, how do I do this? And so what we want to use is what we call the vertical line test. Now, a vertical line is, the reason we use that is a vertical line is simply an x. Okay? So here's a vertical line right there. And this represents all x values. So if x is 1, if x is 2, 3, 4, and so on. So when I run this vertical line across the graph, it represents an x. And what we do this for is that if this line crosses more than one point on the graph, that means I have more than one y for that one x. And remember the definition of function, each x can only have one y. So we run it across here, and notice it only touches one point of that linear equation. That would be a function. Okay, if we take a look at the second one, it's an absolute value. It makes a v. If you run, every time there's a dot. Okay, there's just one dot. It's only touching one, only touching one, only touching one, that's a function. If you look over here at the parabola on its side, what you'll notice is that in this example, we're touching two values, which means there's two y values for this one x. So when x is -1, we have two y's. That is not a function. It does not pass the vertical line test. It touches more than one point. The last one's a discrete relation. Notice it only touches one point, error at 1. Touches only one point at 2. Touches one point at 3. Uh-oh. There's our issue. It touches 2 points at 4. This is not a function. So what we have is we have a yes, yes, excuse me, a no, and a no if they are functions. Okay? And then we could talk about domain and ranges and things like that, and those are all kinds of questions that we can expand on. Okay? Let's take a look at a little bit about functional notation. We'll about wrap it up here. Okay? Functional notation are equations that represent functions, but they're written in a way that we can recognize that they're functions instead of just a regular linear equation or a quadratic equation of some sort. The symbol f of x right there replaces the y and is read f of x. Now, f is simply the name of it. We're naming the function. We could call it a g of x or h of x, like these two right here. A lot of times in computers, you may have like password is the name of the function. And so you send a parameter, you send something inside the bubble. This isn't f times x, okay? It's just naming a function and we're sending something to the function. We're putting something in a function, like what we did with the ingredients. So this is the domain, that's why there's an x there. And the result is the y. So what we want to remember is f of x is the same thing as y. So when I say what's f of 2, what I'm saying is what is the y value when x is 2? Let's go ahead and take a look at some functional notation right here. F of x equals 2x plus 1. F of x is the same thing as y, so technically this is what we have. It's just that it's written in this form so that we recognize it's a function. A function is a special type of relation where each element in the domain is paired with exactly one element in the range. X's can't cheat on the y's. Now what we want to do is evaluate the function at 4. So we're dropping a 4 into the function. So the x, notice what I've done is I replace the x with a 4. So in the function, this is the inside of the function right here. What's the function do? It multiplies by 2 and adds 1. So whatever I drop in replaces the x. So it could be a 4, it could be a 6, it could be a 3 on the next screen. You'll see it may not even be a number. But what you'll notice is 2 times 4 is 8, 8 plus 1 is 9. So what is f of 4 is equal to 9. And really what I'm saying is when x is 4, my y is 9. Those are the same kind of thing. The x and the result is your y. So here, let's go ahead and find f of x is 3x plus 2. Find f of 6 and f of 3. Well, let's do f of 6. Replace the x with 6. See how we replace the x with 6 here? So I replace the x with 6 there. So go ahead and solve. You get 18 plus 2, and you get 20. What is f of 6? 20. What's f of 3? So I'm using the same function, but I'm plugging in a different ingredient. I can use the blender to make a smoothie, or I can make a milkshake. So it's different ingredients. So I'm going to go ahead and plug in a 3, and it's now 3 times 3 plus 2. And so I get 9 plus 2, which is 11. So what's f of 3? That's 11. Okay, take a look at the last examples. What you'll see is the same type of thing. We have f of -1. So make sure we know which function we're talking about. Are we using a blender or are we using a toaster? I mean, that's really what it is. It's two different things. We got to make sure we're calling upon the right thing. So here, we come up here and we grab the f function. Here's the f function right here. And we say, well, look, what I'm doing is I'm replacing the x with -1. And this is functional notation. -2 minus 3 is -5. So what is f of -1? -5. G of 0. Make sure to grab the right one. I come up here. Notice what I'm grabbing now is x squared. So what replaces the x is the 0. So instead of x squared, I got 0 squared. So whatever's in the bubble replaces the x. Okay? So whatever is in the bubble replaces the x in the function. That may be good to get down. Okay? F of a, because notice in this one, notice what I'm plugging in this time is I'm not plugging in a number, I'm plugging in another variable. But that's okay, as long as we understand whatever's in the bubble, that replaces the x. So instead of 2 times x minus 3, Instead of 2 times negative 1, it's 2 times a minus 3. And so we usually leave it just 2a minus 3. And so there you go. There's a result of that problem. The last one, we have g of x plus 1. Again, what's our bubble? X plus 1. So we take the bubble and we replace the x in our g. And so instead of x squared, we have bubble squared. What's our bubble? X plus 1. And you can leave it like that, or if you want to expand it out and FOIL it, you can. It's up to you, but as long as you got to there, I'm in pretty good shape, and you are as well. Okay? That is 2.1 relations and functions. We'll see you next time.